This is Bob Capetta, and this lesson is on truth table proofs. We want to use truth tables to prove the following statement. The negation if P or Q is equivalent to the statement if P is true, then Q is true. Or if you like, not P or Q is the same as P implies Q. To prove this, we're going to use truth tables. So we've got to construct a truth table for two statements, P and Q. And this is typically how we do it, P, T, T, F, F, Q, T, F, T, F. Not P. Whenever P is true, not P is false. So T becomes F, T becomes F, F becomes T, F becomes T. So the not P column is F, F, T, T. I want not P or Q. So for an or statement, as long as one or the other or both are true, the or statement is true. So let's look at these two bits. One or the other or both, yes. One or the other or both true, no. One or the other or both true, yes. One or the other or both true, yes. So the only one that's false is the second one. The others are all true. So that is our truth table for not P or Q. We will also need to construct a truth table for the statement if P is true, then Q must be true. P implies Q. And again, we will start with the PQ columns, TTFF, TFTF. And we want to construct a truth table for if P is true, then Q is true. How do we do that? If P happens, Q must happen. Well, in this case, P happened and Q happened, so sure, that's true. But we're saying if P happens, Q must happen. Second one, P happened, but Q didn't. But we said if P happens, Q must happen, but it didn't happen, so this one's got to be false. And that's our key idea. When you're doing if-then statements, you look for TFs. T in the first one, F following the then. If you get a TF, that result is an F, so this one is an F. Now, how do you handle these last ones? If the first one happens, the second has to happen. I don't know if the first one happens, so I can't say it's false. So anything that's not a TF gets a true statement by default. So TF yields an F. If the first one happened, it didn't, so I can't say it's false. I've got to say it's true. So the statement if P is true, then Q is true gives us TFTT. The statement not P or Q gives us the truth table TFTT. So we see that those are the same. And that is the process that we use to prove that two truth tables are equivalent. So this proves that the statement not P or Q is equivalent to the statement if P is true, then Q is true. So let's look at two of those implication statements and let's construct truth tables for those. So use truth tables to prove the statement if Q is true, then P is not true is equivalent to saying if P is true, then Q is not true. Similarly, Q implies not P, equivalent to P implies not Q. To do that, we need to make a truth table again. P, T, T, F, F, Q, T, F, T, F. Not P. I need Q on the left, which I have. I need not P on the right. I'm going to construct a not P column. The current P is T, T, F, F, so not P would be F, F, T, T. Q implies not P, which means if Q is true, then P is not true. If the first thing is true, the second thing must be true. Well, the first thing is true, but the second thing isn't. That is a failure. So again, remember our TFF rule. We're doing an implication. If you see a TF, the result is going to be F. We're constructing our truth table for if Q is true, then P is not true. TF will yield an F here, but that's the only TF. All the others are something different. All the others are something different. They get trues. So it'll be F, T, T, T is what we get for this one. So that is our truth table for if Q is true, then P must not be true. To determine whether these two logical statements are equivalent, I've got to also construct a truth table for this one. If P is true, then Q is not true. And we'll start that with the same two columns with the PQ column. I want P on the left, I want not Q on the right. So I'm going to copy down the P column, TTFF, fine. Then I'm going to construct a not Q column. If Q is T, not Q is F. If Q is F, not Q is T. If Q is T, not Q is F. If Q is F, not Q is T. So there you go. There's your P column, copied from here. And there's your not Q column, changing all the ones in the Q column. T to F, F to T, T to F, F to T. Now, P implies not Q. If P is true, then Q must be false. Careful. Maybe I better say that instead. If the first thing happens, then the second thing must happen. So our trick for doing implications is to look for TFs. If I see a TF, the result is F. Do I see a TF? If the first thing happens, the second must happen. Here the first thing happened, the second thing didn't happen. That's a fail. Is that the only TF I see? Yes. TF? Nope. The other ones are all okay. So for my truth table, if P is true, then Q must not be true. F, T, T, T. So that is our truth table for that statement. If P is true, then Q is not true. So let's take a look at the two truth tables together, the one we did previously and this one. If Q, then not P gave us F, T, T, T. If P, then not Q gave us F, T, T, T. We recognize they are identical. They have the same truth tables. So what does that enable us to conclude? We can prove that if Q is true, then P is not true is equivalent to saying if P is true, then Q is not true. So let's look at this with some words. John is wealthy or he is stingy. We want to determine if the following is an equivalent statement. If John is not wealthy, then he is stingy. Okay. P is the statement John is wealthy. Q is the statement John is stingy. We're told that John is wealthy or he is stingy. How do we write that using symbolic logic? It's just P or Q using that symbol. And we can construct a truth table for that. Now we have the second part. If John is not wealthy, then he is stingy. We have an if-then, so there's an arrow between these things. If John is not wealthy, it'll be not P, negation of P. Then arrow, he is stingy, Q. Negation of P, arrow, Q. So to determine if these things are equal, what do I have to do? I've got to construct truth tables. A truth table for P or Q, a truth table for not P implies Q, and see if they are the same. So here we go. How about P or Q? We know P, T, T, F, F, T, F, T, F. P or Q, if one or the other or both are true, it's true. One or the other or both, yes. One or the other or both, yes. One or the other or both, yes. One or the other or both true, no, they're both false. If they're both false, the OR gets a false statement. So that is our column for P or Q. Now let's see how we do the not P implies Q. So again, TTFF for P, TFTF for Q, not P. T becomes F, T becomes F, F becomes T, F becomes T. I want the not P on the left, I want the Q on the right, so I'm going to copy down another column of Q to the right of not P, so TFTF. And then we are saying not P implies Q, not P implies Q. How is that going to work? What are we going to do? What are we looking for? If the first thing happens, the second must for an if-then. If the first thing happens, the second must. So our rule, again, our trick was the TF. Do we see any TFs here? Just the last one. The first thing happened, but the second one didn't. That one gives us a false. No other TFs. Those are all trues. So that is my column for not P implies Q, also known as if P is not true, then Q is true. TTTF, for P or Q, that gave me TTTF. What do we notice? They are the same. When they are the same, what is our conclusion? We conclude that the logical statement P or Q is equivalent to the logical statement not P implies Q. But remember, this came from a word problem. So this tells us the following. John is wealthy or he is stingy is indeed equivalent to saying if John is not wealthy, then he is stingy. That doesn't seem automatic, right? I mean, you don't necessarily see that just from looking at the words. So the truth table is a very nice tool to determine if two statements are equivalent. So let's do another one. John is wealthy and he is stingy. Determine if the following is an equivalent statement. If John is not wealthy, then he is not stingy. Okay. We want to use symbolic logic to answer this question. So we'll say P, John is wealthy, Q, John is stingy. Our statement says John is wealthy and he is stingy, P and Q, which looks like this. Fine. Our next statement, if John is not wealthy, then he is not stingy. Not wealthy, so negation of P. Then, arrow, not stingy, negation of Q. It's an if-then statement. So not wealthy implies not stingy. So in terms of looking at this, not P, if not P, then not Q. If P is not true, then Q is not true. So what do we need to do to determine if these two statements are equivalent? Construct truth tables and see how they behave. P and Q, that's pretty easy. P, T, T, F, F, Q, T, F, T, F. P and Q both true at the same time. Where are P and Q both true at the same time? T, T yields T. None of the others have both trues. Those are all F's. Boom. So there's my truth table for P and Q. Now we want to do a truth table for not P implies not Q. If not P, then not Q. So I will need a P column, a Q column, a not P column, a not Q column. But remember, I want the not P on the left, I want the not Q on the right, and what are we looking for? TF, because if the first thing happens, the second must happen. The TF is the failure. If I see a TF, I put in a failure, put in an F over here. All of the others are true. So the only TF is here in the third slot, so TTFT. Are these two truth tables the same? P and Q, TFFF. Not P implies not Q, TTFT. Are they the same? Doesn't look like it. So our conclusion is P and Q is not equivalent to not P implies not Q. So what is our conclusion in terms of words? John is wealthy and he is stingy is not equivalent to saying if John is not wealthy, then he is not stingy. So you can see how this is a powerful tool to break down language. So we need some vocabulary. Our original conditional statement, P implies Q, which of course means if P is true, then Q is true. And then we have the statement that is called the contrapositive. The contrapositive tells us if Q is not true, then P is not true. Can we say that these are equivalent statements? P implies Q. If P is true, then Q is true. There's P, TTFF. There's Q, TF, TF. P implies Q. You look for a TF. Where is the only TF? Second slot. That's the only F. Everything else is true. So there is our truth table for P implies Q, also known as if P is true, then Q is true. Let us do the truth table for not Q implies not P. So Q is TF, TF, T becomes F, F becomes T, T becomes F, F becomes T. There's our column for not Q. Our column for not P, P was TTFF, so T becomes F, T becomes F, F becomes T, F becomes T. There's our column for not P. And I want to do a column for not Q implies not P. The first thing is true, then the second thing must be true. If the first, then the second must be. And our key trick for those is to look for TFs. If I see a TF, then the result is a fail. I see a TF here, TF, that will be a fail for not Q implies not P. All of the others, though, will be trues. The only TF is here, that's the false, the others are trues. So that is my column for not Q implies not P. So let's take a look. We have a column for P implies Q, TFTT. We have a column for not Q implies not P, TFTT. Are they the same? They sure are. So the statement is always equivalent to its contrapositive. So this is important to know. This can also be helpful when we're analyzing language. So if I have the following statement, if Mary studies for her exam, she will pass it. Can you construct a contrapositive? The contrapositive will be equivalent to that original statement. And the way the contrapositive works is you negate the second part, then negate the first part. Negate the second part, she will not pass it. If she will not pass it, then she did not study. what do I say here? If Mary does not pass her exam, negating the second pass, the second part, then she did not study for it. Again, not Q implies not P. That is our contrapositive equivalent to our original statement. If you go to work, you will get paid. Another one, we want to construct a contrapositive, an equivalent concept to our original statement. So negate the second part. If you didn't get paid, then what happened? Then you didn't go to work. So that's the contrapositive. So we have our statement and our contrapositive. So P implies Q is the same as not Q implies not P, which comes up often. Now here's our statement in its converse. P implies Q compared to Q implies P. Now, are these the same concepts? P implies Q, again, what do we say? We look for a TF. If we ever see a TF, the result is F. TF, the first thing happened, but the second one didn't, so the if then failed. TFTT, that's our P implies Q. Now to do Q implies P, I want Q on the left and I want P on the right. So there we go, there's Q on the left, TFTF. I put a P on the right, TTFF. Look for a TF. A TF will lead to a fail on the implication. TF leads to an F there. So Q implies P, TTFT. Are these two columns the same? TFTT for P implies Q, TTFT for Q implies P. They are not the same. The statement and its converse are not the same. Now, what do we know? If the statement and the converse are both true, by the way, that's an if and only if statement. Okay? If I have P implies Q and Q implies P, that's equivalent to saying P if and only if Q. That is also the same thing as saying P is equivalent to Q. So let's finish up our vocabulary here by looking at all four of these concepts. Our original statement, P implies Q. If P is true, then Q is true. Our converse, if Q is true, then P is true. Our contrapositive, which we looked at before, if Q is not true, then P is not true, and the contrapositive was equivalent to the statement. And then the inverse is the contrapositive of the converse. I know lots of vocabulary here, but the inverse is not P implies not Q. If P is not true, then Q is not true. So here is a nice fact to have. The statement is always equivalent to the contrapositive. Boom, boom. So P implies Q is the same as not Q implies not P. So keep that in mind. Try to understand that. And similarly, the converse is always equivalent to the inverse. I didn't prove that in this video, but it's not difficult to do. You can prove that Q implies P is equivalent to not P implies not Q. And that will conclude this lesson.